Hi, I'm Gareth with Nanometer, and this is Ask Nanometer, your technical questions answered in plain English. Today's question, what is voltage drop? Another excellent question that can plague installations with ghosts. Voltage drop can lead to issues as minor as fixtures not running as bright and as catastrophic as driver failure or the entire building burning down. But what exactly is it? You may remember from a previous video we used the analogy of a river to describe voltage and current, and today I want to do something similar. Imagine we have a garden hose with water running through it. In this analogy, the amount of water running through it is the current and the pressure at which it's flowing is the voltage. If we have an unlimited supply of current, or water in this case, the things impeding the flow are the type and size of the hose. This is exactly the same as electrical wire. The conductivity of the wire is determined by the material's rouge and the gauge or thickness of the wire. If the wire is made from copper or silver, it will allow more current to run through it than if it were made out of tin or lead. Similarly, a 24 gauge wire being used for high voltage would be the equivalent of trying to empty a swimming pool through a straw. Voltage drop is not specifically a high voltage or a low voltage issue, just a product of resistance over distance or across components. On the high voltage side, the National Electric Code states maximum voltage drop percentages based on circuit types in order to assure connected load can receive an adequate input power. On the low voltage side, we're both managing our voltage drop between the driver and the fixture and within the fixture itself. The further the distance we intend to travel, the larger and smoother / less resistive hose we're going to need. This is why it's important to check the manufacturer's wire gauge charts so you can see exactly which wire gauge is recommended for the intended distance. Let's take a closer look at the math and the old three-legged stool known as Ohm's law.
Ohm's law tells us that V equals IR, or basically the bigger the resistance, the lower the current on the circuit. In this little example, we've got a couple of little resistors here that are all connected together to a voltage source at 24 volt. We're using resistors here to really symbolize, the other components that you might have on a typical fixture. But this could also be, related simply to the amount of wire that's in place, or it could be, various other components that are doing this. So if we want to calculate the potential difference across each one of these components, R1 and R2, first of all, we're going to need to figure out what the current is, right? And we only know the voltage and the resistance so far. So step one is going to be to make sure that we add up R1 and R2 together. So if we do 47 ohms plus our 222 ohms, that's going to equal 269 ohms. Okay, so that's the total amount of resistance that we have on here. And then if we reconfigure our Ohm's law equation, it's going to be I equals V over R. So we're going to be 24 volts over the top of our 269 ohms. And that gives us I equals 0.089 amps, or 89 milliamps. Now we've got our current for the circuit, we can reconfigure our equation again to get the potential difference for R1 and R2, right? So let's call the potential difference of R1, we're going to call V1. So we're going to do V1 equals I times R, right? I. So in this case, our V1 is going to equal 0.089 amps multiplied by 47 ohms, and that's going to equal 4.183 volts. V2 is going to equal 19.758 volts. So that is going to be the amount of voltage drop, or the potential difference across each one of these components. And there's another little law that you may not know about called Kirchhoff's law. And what he says is basically if we add these two together, that we should get our 24 volts. He says it in a lot more glamorous way. But if we add 4.183 to 19.758, we basically end up with 23.941 which despite a little bit of rounding, basically we're getting 24 volts.
So how is this relevant to the real world? Well, let's take a look at a cuttable constant voltage strip. Each segment consists of various electrical components that induce voltage drop as we work our way down the line. The further away from the input source we get, and the more resistance placed in its path, the lower the voltage will become. This means that a segment at the very end of the run can have a very different input voltage to that of the very first segment and will cause the diodes to perform differently. Perhaps in the past you may have seen a long strip of light where at the end the segments are dimmer than at the start. That is due to voltage drop. I've got two strips behind me. One is a nanometer and one is a non-nanometer brand, but they're both the same voltage, they're both the same output and wattage as well. So we're going to take some voltage readings at both the start and the end of these strips so we can find out how voltage drop is affecting each one. Let's take a look. We'll start by taking a voltage reading off of the non-nanometer strip. We should see that it's right around 24 volts. And we do, this is saying 23.6 volts right now. And now let's take a look at the end. So this is 15 feet later. We're going all the way down and back. Now, let me connect onto the end here. You can see we're reading 21.7. So right around 2 volts of voltage drop is what we're seeing between the start and the end of the strip. Let's take a look at the nanometer one to see if that's any different. Again, you can see we've got 23.7 volts, so right around the same as what we just saw on the last. And now we go 15 feet all the way down and back, and you can see this voltage reading is now 23 volts. So we're only losing like 0.7, less than 1 volt from the start to the finish. Why would one of these strips perform better than the other? Well, the answer is pretty simple. These are both constant voltage products, and as a result, there's a bunch of different electrical components that are needed in order to prevent thermal runaway. You can learn a little bit more about thermal runaway, constant voltage versus constant current in a previous video. Anyway, each segment needs to have something in it to manage the power that's being fed to each one of the diodes in the string. On your typical strip, you'll find that manufacturers just use a simple resistor. This works very well, apart from the fact that at the very end of the strip, we're applying the same amount of resistance as at the very front of the strip. And knowing now that we're going to get voltage drop anyway just from the distance alone, it really doesn't make sense. In reality, it means that you end up achieving voltage drop much sooner because of each segment is knocking off the same amount. On the nanometer strip, things are a little bit different. We've baked in a little bit more intelligence, and we actually use a clever little transistor that sits on each segment. That transistor looks at the input power coming in and it adjusts it accordingly. So rather than having just the same set amount of resistance, it can adjust that level of resistance and change it based on which part of the strip it's going to be on. This means that you don't end up with voltage drop as soon as you do on your standard strips. And exactly what we saw right here. Anyway, that's the answer to the question of what voltage drop is and how it can affect your installations. If you have a question and want an answer in plain English, submit it either on Instagram @nanoltg or send an email to info@nanoltg.com. Cheers and happy holidays.
Ask Nanometer.